let us go back to our volume omega and take a small element here of volume which has a volume of dv and is located with respect to this fixed coordinate system at a point x. So what is the angular momentum of this? The angular momentum of this is the moment of the momentum. So the mass of this is rho dv. This is the mass. The momentum of this is v times rho dv, and the angular momentum is about the origin is x cross v rho dv. This is the angular momentum of this small volume. If I want the angular momentum of this whole red egg, then I need to do integration over the whole volume. So this is the total angular momentum. So angular momentum is moment of momentum. So that is mass times velocity, x cross mass times velocity. So this is the total angular momentum per unit mass would be x cross v. So for angular momentum, is a is x cross v. A is a vector which is x cross v. So that's what we get from here, x cross v rho dv, and ddt of that has to be equal to total torque on omega. Total torque on omega would be equal to, first, torque due to the body forces, so x cross b dv. B dv is the total body force on this small volume, b times dv. Moment of that about the origin gives you the torque due to the body forces integrated over the whole volume gives you the total torque due to the body forces over the whole volume. Similarly, take a small element here. So take a small element of area here, ds. So T ds is the force acting on it. Moment is this. Integrate over the whole boundary, you get the total torque due to the surface tractions that are operating on this volume omega. Add them up. So Newton's second law again for angular momentum says that these two things have to be equal. Okay, so that's where we start from. That's where we start from. This is the balance of angular momentum in vector form. The derivation is just tedious and straightforward. So you have to do whatever you did to the linear momentum. You have to convert this into volume integral, apply the localization argument, and so on and so forth. On the left hand side, you have to take the ddt inside. So we have already done it. So this is your A. This is your A in this case. So you can write ddt outside as rho times dA dt, remember, and A is this quantity. So the left hand side is obvious. The right hand side you have to use the cross product you have to deal with, and you have to convert this integral into a volume integral using the divergence theorem, and then apply the localization argument. The long and short of it, what you will get after this derivation, it will be a straightforward derivation. I am not showing it here because it's quite lengthy. Is this. So what it's going to tell you is sigma ij is equal to sigma ji, which means that stress is symmetric. So sigma is a symmetric tensor, and this fact comes from the balance of angular momentum. There is one small caveat that we want to point out here, that we had body forces which are forces per unit volume. This is what body forces are. We never had any body couples, so we did not apply, we do not envisage that our small volume dv is subjected to a distributed couple as well as a body force. Moreover, we also do not have surface couples. So our surface forces are all forces, they are not couples at all. So this is necessary for us to prove the symmetry of the stress tensor. In cases where body couples are present or surface couples are present, so there are situations where body couples and surface couples have to be taken into account. For example, in situations where your body is subjected to bodies is electrically conducting and sitting in a electromagnetic field. In certain situations, body couples are unavoidable, and in those situations your stress tensor may not be a symmetric tensor. We are considering situations where body couples are not there, surface couples are not there. So in that situation, balance of angular momentum will give us symmetry of the stress tensor. So now we are at least clear about what we need to do. So we now know that we have displacements at each and every point, and there are three components of it. We have strains at each and every point. It's a symmetric tensor. We have six components of it. We have stresses at each and every point. And according to the balance of angular momentum, this is also a symmetric tensor. So there are six independent components. So altogether, you end up with 15 variables at each and every point. How many equations do I have? I have an equation relating u and epsilon. So that's called the strain displacement relation, which is this. This is the strain displacement relation, and there are six of them. There are six such strain displacement relation. There are actually nine, but three are redundant because of the symmetry of the strain tensor. I have also learned that the stress is governed at each and every point. So this equation has to be satisfied at each and every x in the body. I know that stress is governed by the equilibrium equation, which for the quasi-static case is sigma ji comma j plus bi equal to 0. So this is the equilibrium equation, linear momentum balance, strong form of the linear momentum balance, and this constitutes, remember I is the only free index, this constitutes three equations. So I have 15 unknowns. And then I have six equations here, three equations here, so I have 9 equations. I'm short by 6 equations. Where do I get these 6 equations from? That's a question that we will take up after the midsem, but I will give you a small hint now. The hint is this: so far we have used very general principles which are inviolable in some sense. So as soon as you make the assumption that your gradients of strain are small, then this, the strain displacement relation, is a inviolable geometric relation. It appears from geometry, it's derived from geometry, and this is a relation that has to be geometrically satisfied, provided that the strains are gradients of displacements are small. Okay, so it cannot be violated. Similarly, this is a statement of Newton's second law of balance of linear momentum, and this is also inviolable. So far the equations, the 9 equations that we have, are all God-given equations. None of them are man-made equations. They are just embodiments of a geometric principle or a inviolable physical principle. So now what we need to understand is we have never talked about the material. What is this valid for? Is it valid for steel, rubber, chalk? What is it valid for? So, uh, moment you bring in the material, uh, you bring in the human being actually, because the material, what the material is going to do is when you study the material, you are going to sort of generate those remaining six equations that we are missing through what is known as constitutive equations. So constitutive equations are going to connect my stresses to my strains. So the constitutive equations are going to connect my stresses to my strains, and the way this connection is done is not through a physical principle that is inviolable, but through experiments and assumptions about the nature of the material. This is where material science gets married to mechanics. We will of course not, there can be various kinds of stress strain relations depending on the kind of material that you have. We are not going to look at all of them. In fact, we are going to look at only one of them, which is an elastic constitutive equation. And that we are going to take up after the mid-sem.